Um, so, hi guys, uh, let, let's start. Well, um, okay, so uh, we will talk about policy gradient methods. So it's another step in our process part about reinforcement learning. So, and now I want to to see some theory, yes, some lecture material to understand better the practice part of our seminar. So, um, so here we can see so the value-based and policy-based methods. So in the last lesson, we discussed approximate. Yes, and here we um, there we optimized value function or Q function, yes, state value function. So and tried to get the best variant of it, yes, and get the best policy. So today we want to parameterize the policy directly. So, and to find optimal policy just in the policy set. So here we can see some more information about value-based, policy-based, and active critic. I just from scratch, I active critic mechanism just from scratch. Yes, so right behind our seminar. So and I want to test too. So so here you can see value-based methods. Yes, it's when we learn our value function, and we have some policy, for example, like greedy. Yes, but another method is no value function, and we learn on policy. So it's today. So we want to see some methods, some math, so and practice it. So and actor-critic, we learn value function, yes, and we learn policy. So I really hope so. We will talk about actor-critic so later. So let's begin about the policy-based reinforcement learning method. So advantages, of course, we can converge some properties, yes, and we can be effective in some continuing action spaces. So because we learn the policy directly. So and we learn some stochastically, yes. So but we have disadvantages too. So for example, we converge to local optimum, not the global optimum. It's we can do it. So and we have a high variance in a single evaluation runs. So this is disadvantages. So well, policy based. It's just, for example, you have some game, yes, and now, for example, for this state, you have just so to have decision in what move you have to do. So left or right move for this platform, small platform. So of course, for us, yes, for humans, when we see this picture, yes, and we know this game, of course, we know that we have to move our platform to the right, yes, to catch our ball, and so don't lose it. So, but for some algorithm, it can be sometimes really hard to get some state and to generate the accurate, the optimal policy directly. So yes, because policy is the actions, it's the set of the actions. So and okay, Okay, value-based RL. You can see some how function is Q-function, what it gives, and then you have to decide some actions. So from the set of the actions. So, and of course we have some proportional approximation error here. Yes, it's the deep Q network. We tend to minimize this our loss function. Yes, we discussed it in the previous lesson. So, and policy gradient, it's when you want to parameterize our policy. Yes, and then we can find by gradient descent the best parameters of the policy. But what is the objective function of the policy and how we can, because policy is just set of the actions, how we can parameterize it. So, and what do you think about it? So some decisions or some can make it throw out with this, yes, from the set of the actions to some function with some parameters which we have gradient fit, yes, and then we can optimize it by some laws, for example. What do you think about it? How we can do it? Any
Uh,
thoughts? Yes.
like how can we optimize the parameters or
Optimize, I think, by gradient descent. Yes, we can have a gradient, but which loss we have to take such optimization?
I mean, I guess it would depend on the type of algorithm that we want to work with. For example, there is like SAC or PPO, both use different approach if I'm not mistaken. And like there is maybe Monte Carlo policy gradient, which is used by PPO, and I'm not exactly sure which is used by SAC. So I guess it would depend on different type of like approach that we are working with. Or if we are working with like model-based approach, then it would be completely different.
Yeah, you're quite right. So it's but we have some two types, yes, episodic environments and continual environments. So, and this is the differences of it. Is of course we have to see some gradient optimization of these policy just objective functions. Yes, and this is of course it depends on the environment. So, but by the way, so we have our function, for example, yes, and gradient descent. I think it's not really hard task. It's not rocket science. Yes, we have some weights. So and when we can gradient it, yes, and to find some local or global minimum. So, and so here you can see some policy gradient optimization, just loss function, yes, no function for optimization, yes. As you can see, we have some value base, and we can convert it to the policy and Q function. With Q function is with the optimized policy, yes, based on our state and our actions. So policy is the actions, so by the state, and then we have our function. So sometimes, of course, it's difficult. So because we sometimes don't know the distribution of it. Yes, it's the D distribution. Yes, of course, it's computationally expensive because if we have so many dimensions in our spaces, so it's of course it's difficult. So and it's of course it's interactable in some continuous action spaces, so it's hard. So for example, we have first idea, it's to make the numeric approximation. So we can fin it just for definition of the differences, yes, for each axis. and to make, so approximate our gradient. So, but of course we have some disadvantages. So we have noise estimate. It's of course computationally expensive, so we have to make so many runs. So, and of course it's hard to work for some policies. Yes, not differentiable. The second idea, it's Monte Carlo estimation. You're quite right. So, but sometimes um, uh, it's of course it's interactable, but we can estimate the function, so it represents as an expectation some trajectories from the current policy. So, and we have to know this distribution. So, but of course, Monte Carlo estimation is quite better. So, and we can see here log derivative trick. So it's when we just multiplicate and divide by the policy, yes, and to make our log derivative in our gradient. So this is just the math trick math. So, and here we can reinforce our Monte Carlo policy gradient. As you can see, we make just this log derivative trick. Yes, here, and we have the final distribution. Yes, we have a final function where we can take our gradient by the all functions. So logarithm is okay. So, and we can do it for a q function. So, and okay, yes, so it's a log derivative trick. So, and this is the expectation we can estimate by some samples of the episodes. So, here's some better idea. So, and here we can see policy gradient theorem. So this is our result, which we got in the previous slide. Yes, and this is the policy gradient theorem. So about it. About Monte Carlo policy gradient. So with this is the algorithm. So which we want to use in our practice. So it's like reinforce function. So we can initialize and our state is our weights, and for each episode based on the state, action, and reward. So we do the iterative optimization of the weights. So by these policy gradient theorem. So and return the weights at the end. Of course, we have some problems. So because gradient updates, it involves function from the single transition, and it's very, very noisy. So, but of course, high variance in some individual gradient shape, we have it. So, and we can make slower convergence. So, we want to solve it. So, and the idea is to introduce critic model to estimate co-function. So this is the great idea about, I mean, actor-critic mechanism. Maybe you heard about deterministic policy gradient mechanism. So the Google made this model. So pretty, I want to show you, maybe I can find something. Uh, you can see this OpenAI, but of course, here's okay. You can see some anchors. It's the framework of the deep learning based on the TensorFlow. So, and you can see here. Okay, this is the paper. So, deterministic policy gradients, it's a pretty simple implementation of actor-critic mechanism. It's when actor, it makes the actions, yes, of the set of the actions, and the role of the critic have to estimate estimate these action characters. So this is one of the greatest algorithm. I worked with it. So, but it's of course it's 2016, and we know that today we have more more great some examples, more great methods, but it's of course I attention of it. So okay, it's was deterministic policy gradient. So and here you can see. So this is the idea of actor critic mechanism and actor critic policy gradient. And today we want to estimate Q function by some model, some critic model, yes. And as you can see, so actor, it's it can select some policy actions, yes, and critic is the value function. So it's predict the value function. It's the estimate this action. So, and this is the differences between reinforced methods, Monte Carlo, yes, sample policy gradient, and actor critic. So we just estimate policy gradient. As you can see, here we have our gradient by our weights, and this is the gradient by the differences between our weights, but based on the gradients. Yes, and this is the gradient of our function, our policy gradient, so policy function. And but here, as you can see, we have this Q function, yes, of the differences in the weights, so in the parameters. And this is what we can do because we have the second model of the critic, yes, and we can estimate the Q function. So so now just see how we can train it. I think I return to this format. So, and we train it the same way, just deep Q network evaluation and some other tricks. So, just in practice, it's we will see how we can use it. So, and this is the pretty simple algorithm of the actor critic policy gradient. Yes, we can initialize our state, then sample our actions, and for each step we sample our reward, transition, and actions. So, and then we have to just estimate our action. So we do it by here we can see. So the derivative, it's the critical optimization, I think, yes. And here we update our parameters, yes, and then we update our weights. So we end actions too. So yes. So here the great advantage of the actor critic, it's how we can reduce our variance in our estimation estimates, yes, and it's the baseline, yes. So you can see, so the baseline of our policy, we can see this function, so it's go to 0, yes. So well, here about some actor critic mechanisms. So, and I think this is the end. So I want to show you the code. So I had some problems with the code, so I had to update our collab. If we have some questions on the theory part of the lecture, you can ask me. So now, if you have, so and then we go to the practice part. So okay. Today we want to make our policy-based card poll. So our of the carpool method. So by the gym, so let's make our gym state. So so it's, we know it. So already about carpool, we have to just balance this stick. So, and we want to make some simple neural network for a carpool, yes, and just to train it and see the result. So then we move to the actor-critic neural network, but actor-critic, I had no time to test it, so I just wrote it from scratch. So this is the function of the predict probabilities. So we can take our states, yes, by some actions, by our states and batch, and then we turn our probabilities of the set of the actions. So we got our logits from the model, and then we softmax our logits, and we have probabilities. So we tested by some sorts. So, and here we can play the game. So we generate our session. We play full session with some reinforce agent and return some states, actions, and reward. So first we initialize it. Yes, we have our state, we initialize it too. And then we play, yes, for example, just 1000 ticks, yes. And then we got our action probabilities by the above function based on the model output of the logits, yes. We sample some action by the action probes, yes, we have random choice. Then we have our step on the environment, and we got our new state, reward, terminated, truncated, and info about this new state. Then we record, yes, we record our states, actions, and reward. Then we update the states, and so we this is the end of the loop. Just we want to see, so if terminated or truncated, then we break the loop. So then we return our lists with states, actions, and reward. So we can test it by some our environment. Okay, it's great. So we can see what return here the set of our states is, and this is some actions. As you can see, we have only two actions. Yes, I think it's pretty simple, right and the left. So, and you can see the rewards. I think it's okay. It's great reward. Okay. So this is a cumulative reward. I think we discussed it on the previous seminar. Yes, it's when we have to separate. We have to make the maximum, yes, of our reward infinite. Yes, we just finite it, and this is the pretty simple example. Yes, we just have our series of the rewards, and we multiply it by gamma. This is like parameter, so the previous reward. So that's all. So here we test it. Okay, great. So this is the loss function and updates. Our objective function generates on our cumulative rewards. Yes, but we reinforce. We have our reinforce formula. Yes, when we compute the gradient by the expected reward and some policy parameters. So that's it. Yes, and we can use our PyTorch some capabilities, yes, for automatic differentiation of this function, yes, and our objective function will transform to this one. So that's all. Here we can see our optimizer. Yes, and so the grade, we can see, well, we'll see the states and actions. We just initialize it. Yes, and cumulative returns too. So by the torch tensor. We have our logits from the model, of course, based on our states. Then we got our probes based on our softmax. And then we log probes from our log softmax. Okay, so, and we select some log probabilities for chosen actions. So by the torch sum, so we multiplicate one hot vector from the actions, yes, by our log probabilities. So, and then we got the log probabilities for all our actions. We compute our loss here. So, and as you can see, we multiplicate our probabilities to the log probabilities. So this is so this I don't have this formula above, so but we can return to the presentation. Oh, so this is just hmm, maybe this formula was in the previous lecture. So okay, this one. So we just compute our log probabilities and by probabilities. Then the final loss is to multiplicate cumulative returns. This is the cumulative rewards by the log probabilities for the actions. Yes, so we can see the metrics of the log probabilities actions and rewards. So, and we sum it. And then we just add some entropy coefficient. Yes, it's the regularization and the entropy which we computed here. So, and then we make the loss of the minus. So we change our sign. So, and then we have our basic rules for the torch. Yes, optimizer zero radiation, so loss and optimizer step. That's also, and we return our rewards. Yes, our sum of our rewards. So, okay, so this is our function of the train. Okay, works. Great. Here's some record videos. This one. So this is the training process, and we want to increase our mean reward more than 500. Wait a bit. at the end of our training process, it's of course it's for our model, it's harder to make more than 500. So because it's sometimes difficult for it. So we have not so great model. So it's just 3 layers of the simple, fully connected, so just linear layers. So by the way, we just go further in the training process. So and our what increasing. The decrease, maybe it can be overfitting of the model or bad configuration of the model. By the way, we will wait just 1-2 minutes, and then I stopped the training process because 500 we were really near 500 target with the rewards, yes, and this is we have sometimes doesn't matter to be near or more than 500. The result will be great and the result will be good. So, but we'll wait because it's only 5 stick. We have to increase our reward. Okay, great. So it's 500. What's wrong? More. Okay, I think we can stop it. Great. So let's test it and to see the video of the result. So here it is. As you can see, so this small model, based on the 3 layers of the linear layers and the torch, have a great result by the short training. So by the way, we waited, I don't know, just 3 or 4 minutes about it. Yes, and we have a great result. So now I want to try comment this one and uncomment our actor critic model. As you remember, so we have 2 models, actor and critic. So actor, it's we have action probabilities, yes, and with the critic head, the critic model, it's output the state value estimation of based on our actions. So here's this is the implementation of the actor and critic heads. So this is we return just actor and critic functions. Yes, just by within our shared features. So, and now let's try. Let's begin of the just these simple models, just 2 layers, 2 linear layers. So, here we the same generate session the same. So, but we want to have to change our train session. So uncomment. So here So here we can states, some rewards. Yes, we got our logits and states value by the model, model states. Yes, and mhm. I think to make, so here is our model. Station, Adam. So here's our policy loss. We just compute our log probabilities and action log probabilities the same, yes, in minute. But then we have our value function and the total loss, entropy of course too, and total loss, where we just add to the policy loss our multiplication of the value loss and entropy. So this is the regularization type. I really hope it will work. So, okay, problems. I had something the same error before the seminar. I just update. But sometimes it's with it. I don't exactly know. So is it? I don't exactly know the same error it is or not. I will try to reload or collab. It's a very strange problem. It's when I can't just update the yes and just or reuse my environment. Yes, because the error is safe. I don't know why. So I had the same problem before summer, and it was some situation because 2 hours above 2 hours before I started this notebook and everything was okay. Maybe after video generation or video rendering by the gym, something can go wrong. I know it, and I know I had some bad experience with video rendering by the gym. Everybody knows, so sometimes it's have some bugs. So maybe it is after video generation, our notebook maybe reuse or I don't know, save incorrect some parameters. But of course, I know this can be this error can be through my bad maybe implementation of the actor-critic mechanism. Maybe. So now we will check it. So and maybe we will edit some implementation of the actor-critic mechanisms and see how we can reuse our action probabilities. So in generate session function. So Um, So we'll see, generate our actor and critic states. Okay. So predict abilities. Oh, strange. Because it's the same code which we had in the previous version of this notebook. And as you can saw, everything worked. And here we
I
don't
think
use.
I think if you're not using a seed, then sometimes the model can output some NaN values for action. And if you try to like maybe print the action, you'll see what's the problem.
Here's our tensor. Okay. Well, okay, just maybe we try to approximate the previous one model. Yes, we have some dim and actions. Yes, and okay. Here we can see something similar. If we use our model, multiple views. I see. So here we just, this is not obvious. So here we another just another shape of um, our prediction of the model. Okay, okay. Well, I think just we have to use something similar, something this one, maybe, or not the tensor.
I think you can write comma 0 after 0 and it should work.
Yes. Mhm. Right. So this is some problems when you implement some new models. So when you want to just I think we have to delete this string. So here the same function of cumulative reward. Okay, great. So and optimizer. Optimizer we have the same. So Adam, and here let's try to use train on session. Here maybe something goes wrong. Yes, it's wrong. Separation. Oh, okay, it's when we generate session, want to. I see. So our problem is so we have some torch concatenation here, yes, but it's not works with NumPy arrays. So and when we have to use this one. So I think we can just make from the NumPy arrays to the torch to the torch tensors. So where it is, it's the rewards. Train session. So this torch tensor. Okay, I think strange because we have our states rewards arrays. So, but I think we have to make so like here we use maybe torch tensor for our rewards. But maybe it will works. Check rewards and gamma. I think it's the point next values. Next values in the torch tensor. Okay, we'll just make this one. So yes, so we first of all we have our torch tensor of our state values. So everything have to be okay with it. So but rewards we have NumPy array. So and this is why we couldn't summarize so NumPy array and our torch. We have in the torch. I think we can. So and of course to make our type. Maybe it will works. Maybe. Okay. Great. It works. So even you can see so our rewards increase. not so quickly as in the previous model, in the light model, but I just want to remind you, so here we have two models, critic and actor. It's bigger and we have to have more time for training it. It's just the obvious just I don't know. It's obviously for that you have you have to generate more time for training the larger model. So we will wait some minutes, don't know, so maybe 3 or 5. So then I think we can interrupt our training process. Maybe after 300, 400, it will be okay. So I don't exactly sure. So we can so got the result of what's above than 500, but maybe more than 200 or 300 it will be okay. So let's see. So you can see sometimes the reward suddenly uh, decreases. So it can be if critic had some other turns. So yes, or actor generate some wrong actions. So sometimes it can be because in actor and in the critic we have not so great models. Remind you, so it's even it's just 2 models. We have just 2 linear layers in actor by the hidden dim, so 16. It's not so great, yes, and just 2 linear layers, so in the critic model. So, and well, um, sometimes it can be not so smart, I think. By the way, we want just compare this basic simple version of the actor-critic mechanisms, yes, with the policy gradient one, yes, policy gradient method model, simple model with 3 layers, linear layers. So one just compare it. Mhm. I think we can wait when rewards will be stable, a bit stable, not decrease so significantly. Okay, so we won. Great. So let's see if results will be rendered. So I really hope of it on it. So we record some sessions. For me, it's very interesting to see the results and compare it with the previous. I just make a new code. So here we can play. I remind you so how our policy gradient method worked. Yes, not so bad. So I think it's pretty good. So and now render the new one based on the actor critic. Something the same. Nice. One more policy gradient. seconds, and actor critic. For me, maybe is the minimal differences between them. Both of them goes to the age of the sector, but it's completely won the game. So I don't know if you have some thoughts or opinions about these two methods. So, well, let's discuss. Let's discuss. So, by the way, this is all. This is the end of our seminar. So that's all what I wanted to show you. So, if you have some questions of the model or policy-based grading methods or active critic, you can ask me. So now in the chat. So if you want, so you can do it. 3, 2, 1. So if you have no questions, so thank you so much for this seminar. Thank you for visiting it. So goodbye. Goodbye. Have a nice day.
Thank you.
Bye.